Hello, everyone. Good morning or good afternoon, depending where you are in the world. And welcome today to this exciting webinar on quantum nanotechnologies, future challenges and research directions. This webinar is based on the roadmap on quantum nanotechnologies, published on Nanotechnology early this year. Since its publication, the roadmap has been one of the most read articles in nanotechnology, with over 27,600 downloads. Thank you very much to all the authors who have contributed to this excellent piece. Today, we're going to be offering an overview of the roadmap, as well as an exciting talk from one of the authors, Dr. Joe Salfi. The talk will be then followed by a panel discussion on the future of quantum nanotechnologies, moderated by Professor Jonathan Bao, with Dr. Joe Salfi, Dr. Adina Leukenmeyer, Dr. Fernando Gonzalez-Zalba, Dr. John Moll, and Dr. Adam Weissen as panelists. Before we start, I would like to briefly direct your attention to the link in the chat function, which will take you to Slido, where you can post your questions for the panelists. Please do so now. You can also vote for your favorite questions posted by others, and we will try to answer some or as many as possible over the course of the webinar. I'm now going to hand it over to Jonathan Bao, who will be facilitating the speaker session first and the panel discussion after. Jonathan Bao is an associate professor at the University of Waterloo and a member of the Institute for Quantum Computing. He has worked in the field of magnetic resonance, quantum information processing, and nanoelectronic devices. His current research focuses on quantum transport in nanostructures and the development of scalable quantum devices. He is a member of the executive editorial board of our journal, Nanotechnology, and one of the lead authors of the roadmap. So, Jonathan, over to you.
Thank you, Piera. Let me just share my screen here. Oops. Okay, so yeah, thanks again, Piera. So I'd like to briefly walk through the topics that were covered in the roadmap. And let me just start by acknowledging my co-editor and co-author, Arne Locht. So Arne played a major role in putting this all together. He's in Australia right now where it's 4 a.m. So this is why he couldn't join the webinar today, which we completely understand, of course. Now, the roadmap was published in early 2021, but it was actually conceived in 2019, which happened to be the 60th anniversary of Richard Feynman giving his famous lecture, "There's Plenty of Room at the Bottom." He gave this talk in 1959 at a meeting of the American Physical Society in Caltech. And it's regarded as the first lecture by a major scientific figure on technology and engineering at the atomic scale. Now, the term nanotechnology was first coined in the 1970s, but the field didn't really take off until the 80s. Now, the journal Nanotechnology, which is the reason we're all here today, was founded in 1989. So 2019 was also the 30th anniversary of that particular milestone. Okay. Oh, yeah. Sorry, I should have gone to this slide here. Now, the early 1980s also saw the genesis of another revolutionary idea, which Feynman also played a role in, of course, the idea of using the laws of quantum mechanics to process information in a way that classical physics does not allow. For example, using one quantum system to simulate the physics of another quantum system, which is what Feynman suggested, or using quantum mechanics for secure communications, as proposed by Bennett and Broussard in 1984, or conceiving of a computer to run quantum algorithms, pioneered by David Deutsch, Peter Shor, and others in the 80s and 90s. So quantum information in science and technology has seen explosive growth as a field over the last 20 years. And of course, it's now widely pursued in both academia and industry. Now, quantum information at first sight might seem abstract and theoretical, but at the end of the day, you need physical implementations to make quantum technology a reality. The idea of this roadmap article is to highlight the growing convergence of these two fields, recognizing that nanotechnology is really helping to shape the field of quantum technologies. at least for an important subset of implementations. Now, of course, it's a two-way street. The drive to develop quantum functionalities is providing new tools and new capabilities for manipulating and understanding matter at the nanoscale. So nanomaterials and nano devices are being used today as building blocks for quantum computing, as sources, detectors, and memories for quantum communication, and also for quantum sensing and metrology. All right, so this is a broad and rich field, and so it wasn't possible to cover everything in one article. We focused on these 7 areas, which I'll go through in a minute, in order to give a fairly wide cross-section of the field. Each of the contributions were written in a kind of forward-looking way, right? So not only providing a picture of the state of the art, but also focusing on the future challenges and opportunities that the authors saw. Okay, so the first topic that was covered is metrology and sensing. And so there we had 2 contributions, one by Fernando Gonzalez-Alba and David Riley. Of course, Fernando is on the panel today with us, and the other by Holz and Ubelode at PTB in Germany. And Fernando's contribution was on fast dispersive readout for solid-state qubits, and the other was on quantum metrology with single electrons. Okay, now in the section on quantum light sources, cavities, and detectors, we had 2 contributions, one on quantum light sources by Staub and Schroeder, and the other on semiconductor superconductor hybrid circuit QED by Scarlino and Koski from ETH Zurich. We had a 3rd section on quantum computing with spins, and here we had several contributions. So the first was on gallium arsenide quantum dots by Kumuth and Bloom from Germany and Denmark, and then quantum computing with spins in silicon quantum dots by Zurak, Yang, and Yoneda. They're from UNSW, and they're colleagues of Arne Locht. We also had contributions on quantum computing with donor spins in silicon by Pla and Hill, also from UNSW, and single atom qubits, focusing on acceptors by Joe Salfi, who of course is our speaker today, and I'll introduce him in a minute. And then finally, we had a contribution on photon spin interface by Akira Oiwa from Osaka, Japan. Okay, and the next section was on nano and optomechanics, and we had contributions on opto and electromechanical transduction from Muhonen and Verhagen, Finland, and quantum nanomechanics from Matt LaHaye. Then we had a section on low dimensional systems with a contribution from Cam and Adam Sen. Of course, Adam Sen is on our panel today. This was on 2D magnetism in magnetism in 2-dimensional semiconductor systems. And the other contribution focused on 1D systems hosting topological states by Kolser and Gurezdi. And then we had a section on molecular devices with a contribution from Jan Moll, who is on our panel today as well. And then finally on nanoplasmonics from Mohan and Jane from Illinois. Okay, so those are the topics that we covered, certainly not exhaustive, but it gives you an idea of the types of systems that we have in mind when we use the term quantum nanotechnologies. Okay, and here is the DOI for the paper in case anyone in the audience hasn't read it and would like to. It's open access, so anybody in the world can access this. Okay, and so with that, I would like to now introduce our speaker today, Joe Salfi. So Joe's an assistant professor in electrical and computer engineering and a principal investigator at the University of British Columbia. He's an expert in the physics and technology of spin-based devices and leads a research group that focuses on scalable quantum computers and quantum simulators. And today he'll tell us about single atom qubits. So thank you, Joe. And I'll stop sharing my screen here. You can take it away.
Thanks, Jonathan. Thank you very much for the introduction. Can people hear me? I hope so.
Yes.
Oh, great. Thanks for confirming. So do you see right now you see probably not the one you're supposed to. Oh, no. You hopefully, yes. Okay, good. I think you do see the slides correctly as well.
Yeah, it looks good.
So I didn't hear that, Jonathan. Sorry.
Oh, yeah, no, it looks good. We can see your title slide.
Okay, thank you so much. Great. This is my first time using GoToWebinar. Great. So thanks again for the introduction. And yeah, I'm going to just dive in. So this talk is about single atom qubits, and I had to decide a little bit how to scope it because it's actually a fairly large topic. Since this is a special issue on nanotechnology, of course, I'll be focusing on the solid state, but I wanted to give credit to where I think a lot of the ideas in this field really come from. And hopefully, I'm trying to use the pointer now. And I'm wondering if that's working. I don't think it does. It was working when I tested it before. Okay, so in the bottom, on the left-hand side of the screen, I'm showing, I think what I think is the first proposal for building quantum computers with atoms, and those are atoms in a vacuum. And this approach uses ions trapped in an electromagnetic trap and lasers to control and measure them. And there's been a tremendous amount of progress in this system since it was proposed a long time ago in 1995. You can see what the technology looks like in the photo on the bottom left, which is that it's a rather large, it's a macroscopic system, a few millimeters long, and there are ions trapped in it whose fluorescence you can measure and which you can focus light on. So as Jonathan alluded to, the nanotechnology is very different from this. It's a very small scale devices or structures down to the level of atoms. And what I believe is the first proposal for quantum computing with atoms was proposed in silicon. And it's called the Kane proposal from 1998, and that's shown on the right-hand side. And here, the idea was to incorporate these 31 phosphorus donor atoms into a silicon host here, and that we could fabricate actually metallic gates on top of it, just like transistors. Okay, great. And that these electrodes would actually allow us to control the electrons and nuclear spins on those individual atoms. And this was a proposal for an atomic level nanotechnology from 1998. And when this was proposed, we actually didn't really have any way to really do this. And that was certainly a valid criticism of this proposal. But the reason why it was so interesting is because the states, the electron and nuclear states inside of bound to phosphorus donors have some very interesting properties for quantum computing. Namely that it was anticipated that they would be extremely coherent, or that two-level superpositions created with that would have very long lifetimes, which is one of the key big challenges in quantum computing. Okay, so then if there was no way to do that when it was proposed, then how has that been developed? So the first demonstrations of quantum computing, quantum single atom quantum devices were achieved in 3 different platforms. And what was demonstrated was a phenomenon called Coulomb Blockade through these single dopant atoms. And what Coulomb blockade is it's a phenomenon whereby electrons flowing through some kind of localized state this happens one electron at a time. You can't put 2 electrons on that site, or you have to pay a price, which is the Coulomb energy. So in 2006, this Coulomb blockade through single atoms was demonstrated actually first in a very small industrial transistor, because at the time it was realized that these devices, as they get smaller and smaller, would in fact, the graininess or the discreteness of atoms would start to manifest itself. Then, so this was accomplished using transistors from a foundry IMEC in Belgium at TU Delft by Sven Rogge. And then later on at UNSW in Sydney, Australia, 2 other techniques were developed inside of university fabrication facilities. The first was the ion implantation, where these atoms were, accelerated, the phosphorus ions were accelerated and implanted inside of a crystal underneath a gate that's used to control the transport. And then this extremely impressive demonstration of fabrication at the atomic level using a scanning tunneling microscope was demonstrated just 2 years later for a single atom. So what really, another big development was the ability to read out the spin on a single atom inside of one of these transistors. And it was accomplished using a standard approach taken from quantum dot, a different field called quantum dot, basically research. And this uses something called spin to charge conversion. The reason for that is that the magnetic moment of a single electron is very small, and it's hard to measure quickly. However, charge is relatively much more easy to measure using electrometers, single electron transistors. So you have a single electron transistor here, and then proximate to that, you have a few dopant atoms. And I'm not going to go into too much detail other than to say that one of these spins, electron spins on these atoms, can tunnel to the single electron transistor. And by doing so, the single electron transistor will see a different amount of charge on this collection of dopant atoms. And that allows you to read out the spin degree of freedom, because the motion of the electron spin to the single electron transistor, it depends on if the spin is up or down. And that's because of the Pauli exclusion principle. So this was a big development, the ability to measure just a single atom's spin using spin to charge conversion. And what it allowed was actually for electron and nuclear spin qubits to be demonstrated on these phosphorus atoms in a series of papers published in Sydney by Jared Plough, who's a co-author of this, one of the co-authors of this roadmap. So, given that one of the motivations for Kane's proposal was to realize very long coherence times, we can ask this question, as of 2011, we could ask this question, just how good are silicon qubits? So in particular, they become very good when you remove the nuclear spin-bearing isotopes from the material. And sometimes they've been called atoms in a semiconductor vacuum. This isotope purification removes nuclear noise, the spin noise from the nuclei. And devices have been demonstrated, ensembles have been demonstrated with 10 to 100 millisecond electron coherence times. This is very long for a solid state system. It's close to the record. And then also for single donors and quantum dots in this isotope purified material, in the devices, these long coherence times are maintained. Okay, so what is the state of the art today? What does it look like? So we know that in quantum computing, if you want to make a quantum processor, errors are extremely important, minimizing errors. So donor qubit measurement has been achieved with very, sufficiently low errors below, say, a threshold that of importance for a certain type of code. Donor single qubit gates have been realized with very low errors, and there's a paper on the archive from Australia from Andrea Morello's group demonstrating, kind of the actual one of the main challenges in the Kane proposal, which would be to entangle the nuclei of two adjacent phosphorus atoms, to entangle them so that their properties are highly interdependent on each other. And this was done with an error of around 1%, so a fidelity of around 99%. And this looks a lot, this cartoon here, these are drawings, but they represent what is happening in this experiment, and it looks a lot like what Kane proposed, which is now 24 years ago. So there's been an incredible amount of progress in this field. It's kind of amazing, actually, that you can control electron and nuclear spins of single atoms with a device. Okay, so the summary is that there are small and very clean qubits in silicon, single atoms. However, what are the challenges moving forward? Are we done? Given that this experiment has been done and errors of around 1% have been achieved, are we done? Can we, say this is going to happen, a single atom nanotechnology? And unfortunately, the answer to that is, of course, it's not clear. And one of the main challenges is the short range interactions. So, and they're problematic from a few different points of view. One being electric noise, another being if you just put these atoms very close together, they will have a lot of, there's a challenge in controlling each one of them. There's a lot of high density, and when you control one, you may be accidentally manipulating another. And not to mention that this is just very difficult to fabricate these kind of devices. And by short range, I mean something like on the order of 20 nanometers for donors, so single atom qubits, and 100 nanometers for electronic quantum dots in silicon, so that a different type of technology. There's an additional challenge in silicon, which is a so-called value degree of freedom, which actually myself and Jan Moll, who's also on the panel discussion today, we imaged the oscillations in the charge density that come from this value degree of freedom for the first time, a few years ago. And this really verified that this process of the processes introduced by the value degree of freedom of electrons, this could cause a serious problem in quantum computing. Okay, so I'm now, I think, roughly 10 minutes in, so I'm starting the actual talk, which is usually, a pretty good, a pretty good rate. So let me tell you about the work in the roadmap on acceptor qubits. So what do we want to have in a single atom qubit? So definitely we want to maintain the long coherence time that allows us to keep errors, to minimize errors. But there's a lot of work today on single atom qubits in terms of building a long range but noise insensitive way to connect qubits together. And there are a few different types of ways to do that. One could be, for example, capacitive interactions, or another could be quantum electrodynamics with, for example, phonons or photons. So that's, quanta of light or quanta of sound in a chip. And I just highlight here one particular proposal that I'm going to talk about today, but there are many. So then the question is, how do we actually accomplish this? And from a technical point of view, what it means is enable electric control of, or elastic control of spin, and do it without spoiling coherence. So why is this hard to do? So the first reason is that silicon electron spins have very weak intrinsic spin orbit coupling, and that's usually one of the reasons that their long coherence times are attributed to. Or in other words, electric coupling is normally associated with destroying coherence. So, this is not a new story. This is the story of quantum computing. If you want to control something, you expose it to noise. So just reviewing the two ways in which this electric control that would enable long range coupling can be achieved. The first is building an artificial electric dipole. So you take a magnet that's a nanoscale or micron scale magnet, you put it near a qubit, and then you induce a motion of the electron. And because the magnetic field produced by this magnet is inhomogeneous, the electron feels a time-varying magnetic field that can drive it. And this was first demonstrated in gallium arsenide, later in silicon, and it works pretty well, but it definitely sacrifices coherence. Then another idea that has been around for a long time, probably first mentioned or published on by Daniel Loss, is using the intrinsic electric dipole of a particle in a solid that arises because of special relativity or the intrinsic spin-orbit coupling. However, the story here has for a very long time been very bleak, which is that coherence times will be suppressed by 5 orders of magnitude. And trying to use this for electrons in silicon would be difficult because it's just very weak. Okay, so the existential question for spin orbit qubits is 1 microsecond coherence time really the best we can do with it? Or maybe a better question is, how do we keep spin qubit coherence and keep strong intrinsic spin orbit coupling? And what this would do if we use whole spins, which I'm going to talk about, the platform we are investigating in the work I'm presenting, is it would make this a simple candidate for scalable quantum computing. Unfortunately, the conventional wisdom is this is simply not possible to do because, well, I should have provided a reference here, but for example, Burmester's paper from 2014 with Dimi Kulsar. So in this talk, I'm going to show you first a little bit of theory and then experiments demonstrating that you can keep strong intrinsic spin orbit coupling and coherence at the same time when the spin orbit coupling is strong enough in a J=3½ system. That's a little bit counterintuitive. So first, let me talk about the system. So it is a hole, a valence band hole. It has orbital angular momentum of 1 and an intrinsic angular momentum of 1/2. And so through the L dot S term, the actually total angular momentum of 3½ gets quantized. And we're not talking about electrons in the conduction band, rather we're talking about holes that occupy this valence band. And first, Charlie Tahan and Rusko-Ruskov pointed out that through interactions of the isospin or the spin in the valence band with phonons or sound in a crystal, that you could use this sound in specially tailored structures, very highly engineered materials to make long-range interactions mediated by individual phonons, and that these qubits would have long T1 times, relaxation times. That's a rather complicated picture, so I'm just going to skip through it. So then our proposal, we took Tahan's idea and said, oh, what if we could convert that to electric control? So the things we wanted to keep the long-range interactions, but we wanted to mediate it electrically or with microwave photons. And additionally, we set the criteria that the coherence time should be long. So now I'm going to talk about how that idea works. The idea is basically that when you have a valence band hole, there will become 4 states that you're interested in instead of 2. And they have different projection of total angular momentum onto the quantization axis. They could be +3½ -3½ +1/2 and -1/2. And then what's very interesting about this system is and this is actually probably where the idea, the genesis of this coherence idea comes from with holes, is that those terms couple through electric and elastic quadrupoles. And anytime there's a coupling, you can get an avoided crossing. And these avoided crossings are what produce clock transitions in, for example, atomic clocks. So in an atomic clock, you have a magnetic clock transition. It's a point where the splitting between 2 levels doesn't depend on a fluctuation in a magnetic term. Well, we found the same physics for fluctuations in electric terms within this 2-level system. And the outcome of that was we theoretically predicted that 1 high fidelity 1 and 2 qubit gates would be possible in that system, and that it would be robust to electric field noise. This is exactly what we were hoping to find, and it turned out that in this simple system that could be observed. So moving to the experiment, what we did is we used strain to introduce a splitting between these two different levels, because we have to have a well-defined qubit. And then we used isotope purified silicon to remove the nuclear bath. And then we basically flipped a chip on top of a superconducting resonator. So here's the silicon chip, and here's the superconducting resonator. And we measured T2 with Hahn echo and with dynamical decoupling, and we measured spin relaxation. So I'm going to go through the results very, very quickly. First, we identified the levels spectroscopically in the strain sample with no strain and the sample with small strain, and we found them where we were expecting them. And then the big key result is that in the unstrained device, where we have essentially, this is like kind of a charge qubit with these -1/2 and -3/2 levels, we could actually achieve an unexpectedly high coherence time around 20 microseconds. And then in the strained device, where this strain splitting here turns out to be around 50 gigahertz, we could find a 1 millisecond coherence time. And the key is this Hahn echo coefficient, the stretched exponential coefficient of being 2.5. And this tells us that slow fluctuators are dominating our decoherence process. And that means that if you apply dynamical decoupling, you should get a longer coherence time. And indeed, that's what we saw, around 10 milliseconds. So the sort of take-home message of this is that, we knew going into this study that, we could push the coherence time up to around 100 milliseconds for electrons in silicon bound to donors. The outlook before this work looked very bleak for whole qubits, around 250 nanosecond coherence times. And we could improve this by around a factor of 10 to the power 4, 10,000 to 100,000 improvement over previous spin orbit coupled systems. I'm running out of time, or I may already have run out of time. So I just want to point out that there's also been some work that I've been involved with a PhD student, Joost van der Heijden, and Del in UNSW, looking at single atom devices. Okay, so these devices can also be made. Another point I want to highlight now is our recent theory work showing that this effect of being able to find these optimal operation points, it's generic to which any material you want in group 4, meaning it has a Rashba and no Dresselhaus, and it also doesn't really depend on what's confining the hole. It could be an impurity or a quantum dot. So just to summarize this, what we found is a J equals 3/2 system that's nearly as coherent as a spin 1/2 or a spin 1, so diamond or silicon donor. This is highly non-trivial because of the spin orbit coupling, and the opportunity here is very appealing. It gives us another platform within quantum devices, with namely whole qubits, to try to build scalable quantum computers, where I've tried to make the argument that because of density, crosstalk, fabrication difficulties, and noise, it's very appealing to go to long-range gates. And the key is really these kind of optimal operation points in the future that we're looking at. So I just want to thank my co-authors on this work, and finish by noting that if you're interested in this type of work, my group we've just built a lab at UBC in the Quantum Matter Institute, and we have a number of interesting projects on quantum simulators and spin-based quantum computing. Here we're actually using quantum dots and assisted by superconducting technology. So with that, I just want to thank you for your attention and open up for questions.
Okay, thanks very much, Joe, for a really nice talk. So, people in the audience, feel free to type your questions into the Slido that's given here in the comments. maybe I can start off with a question or two. So you have this effective electric dipole coupling that you can achieve between two acceptor qubits. Does that work simply through a capacitive coupling? So, for example, you could have a floating gate that's connecting two of these. And if that's the case, sort of what is the typical link scale that you have in mind for this long range coupling?
Yeah, thanks for that question, Jonathan. Yeah, so the Coulomb interaction, it is the Coulomb interaction between the charges on the two qubits. So that's indeed, it's a capacitive interaction, and that maps into the spin sector because of the combination of spin over coupling and the Zeeman interaction. And that's a very well, that's not something that we invented. That's been known for many years. So indeed, it can be done capacitively. And then the question of how far is an interesting question, because sort of what we found by looking at numbers of this sort of bare Coulomb interaction is that you could extend the range by like a factor of 5, but I think what you said there is really key, is that if you put a floating gate and reduce the stray capacitance of that floating gate to other things, then the distance can actually be surprisingly far, like on the order of a micron is doable. And then there are in this kind of a scheme, you could imagine pushing them that far apart. And then of course, if you want to have some kind of very long distance coupling, then there are other ways to achieve that, but you wouldn't do it capacitively.
Okay, great. Thank you. There's one question from the audience, which I'll just read out. So what can be the highest possible clock speed frequency reached using this technology? And are there effects of noise observed, such as jitter and skew?
Yeah, thanks for that question. So in quantum computing, I would say it's convenient to work in a range of, I would say, something like tens of nanoseconds or hundreds of nanoseconds. We don't really like to go much faster than that because it's difficult and probably doesn't get you that much. Like probably, I mean, the question in quantum, manipulating quantum systems is not just how fast you can do it, it's how accurate you can do it. And sort of the combination of accuracy and speed is important. So you would, start to compromise accuracy at the if you start going, a lot faster than something like on the order of 100 nanoseconds. So this kind of idea that comes from maybe classical electronics, that going faster is better, doesn't seem to translate to quantum devices. That would be my answer, but I'm curious what other people think.
Okay, yeah, that sounds great. I believe that Fernando Gonzalez-Alba on our panel has a question. So Fernando, go ahead.
Thank you very much, Joe. Great presentation. I just had a question about your previous slide, your work on germanium-based spin orbit qubits. You mentioned that you work on a theory project on finding sweet spots of operation. Can you comment a bit more on that? Whether they are also based on engineer stress, as your boron demonstrations?
The strain doesn't really matter. It works with or without strain. We have a paper that's going to come out soon about that, but we've looked at different strain, different materials, and we've incorporated like effects from realistic devices, so like actually CAD based design, and that work will be It's about to be submitted. So it survives under a surprisingly large different array of like circumstances. It's universal, I guess is the way to put it.
Okay.
At least it's a universal aspect of the theory. So experiment, takes a long time to actually show those things. So it was sort of 4 or 5 years between the theory of the whole acceptor, whole qubits, and the demonstration. So.
All right, great. I don't think there are any more questions from the audience, but does anyone else on the panel have any questions for Joe? Okay, well, if not, thank you very much, Joe. That was a really nice, enlightening talk. So maybe what I'll do now is just introduce the panelists, and then we can move on to the panel discussion. So let me start with Fernando Gonzalez-Alba. He heads the quantum hardware team at Quantum Motion Technologies, a UK-based startup dedicated to the development of quantum computing hardware based on silicon technology. Fernando is also a UKRI Future Leader Fellow, Associate Lecturer at the University of Cambridge, Research Associate at University College London, and Quantum Fellow at Hughes Hall at Cambridge College. Quite a mouthful. Fernando's research focuses on a variety of topics, including single atom electronics, quantum sensing, quantum limited amplification, cryogenic classical electronics, and new computing paradigms such as quantum computing. Okay, and then we have Adina Lupin-Meyer. She's an assistant professor in the physics department at University of Ottawa since 2016. She received an undergraduate degree from Jacobs University, Bremen in Germany, 2006, and her PhD in physics from Rutgers, 2012. Prior to joining University of Ottawa, she was the Alexei Abrikosov postdoctoral fellow at the Center for Nanoscale Materials at Argonne National Lab. Her research group focuses on uncovering the novel electronic properties of low-dimensional quantum systems using scanning probe microscopy and supporting spectroscopic techniques. And we have Jan Mol, is a reader in quantum and nanoelectronics at Queen Mary University of London. He's previously worked at the Kavli Institute for Nanotechnology in Delft, the Center for Quantum Computation and Quantum Communication and Technology in Sydney, and at the University of Oxford. His research spans a wide range of topics from molecular biosensing and data storage using solid-state nanopores to single molecule electronics and quantum thermodynamics. Okay, and then we have Adam Weissen. He joined the Institute for Quantum Computing in the Department of Chemistry at Waterloo as an assistant professor in 2016. After receiving a BS in electrical engineering and computer sciences, as well as a BS in engineering physics at the University of California, Berkeley, he completed his PhD in applied physics at Cornell under the guidance of Ji-Woon Park. Wei then joined the Department of Physics at Columbia University as a postdoctoral associate with Abhay Pasupathy and Philip Kim, where he studied atomically thin quantum materials and incorporated them in nanoscale electronic devices. He continues to explore these materials at IQC and develop novel quantum devices based on their exotic properties. And of course, we've already met Joe Salfi, and he's sticking around to be on the panel as well. So, so again, I would just ask people on the audience to type your questions into Slido, but maybe I'll start off with a few questions targeted to some of our panelists just to sort of get things going. So maybe I'll start with Adina. So you've worked with Moiré superlattices in graphene, and I know that those superlattices in graphene and other 2D materials have attracted a lot of attention lately as a new method for realizing unconventional electronic states in quantum materials. Can you talk a little bit about the kinds of states that people have been able to engineer in those systems, and what are the potential applications that you're most excited about for these quantum materials?
Yeah, sure. So in this field of twisted 2D materials started almost serendipitous in 2009 when we found out that they can alter the properties of the material, just a slight twist between two planes and atoms. But it wasn't until later, so approximately, quite a number of years, 5 years later, that it was found out that the band structure can be changed in such a way. So this twist changes the interlayer coupling, and it can change in such a way that it gives rise to flat bands. And so that experimental realization and the theoretical proposal came a little bit later, and it was then that sort of boomed this entire field. And on a material preparation side, it was because we learned how to make very precise stacks of 2D materials with very well controlled angles of rotation. And so since then, in just a couple of years, these flat bands in twisted graphene, twisted boron nitride, twisted transition metal dichalcogenides, have really checked every chapter in your many-body physics books: superconductivity, magnetism, and you name it. So I guess to keep it short, what's probably most exciting to me is the idea that you can use them as a quantum simulator. The fact that you can create these super lattices where you can tune the coupling between the sides of the Moiré pattern. So it's already demonstrated that a Hubbard model can be sort of mimicked by these Moiré patterns, and you can do the readout with techniques like my group does, scanning probe spectroscopy or maybe optical techniques. And this space is quite unexplored. So the symmetry of the crystals, the Moiré crystals, you can create is quite unexplored. So I would say that's probably an exciting direction to go.
Okay, great. Thank you. Let me move on to Fernando. So in the roadmap, you wrote about fast, high-fidelity readout of solid-state qubits. And we know that that's critical for scaling up quantum computers and simulators. You nicely described the many advantages of gate dispersive charge sensing and the physical limitations on it. So if you think of something like quantum dot spin qubits, for example, how far do you think the minimum measurement time can be reduced realistically? And what's the ultimate limiting factor on that? And then second part of the question is, for scalability, you also talk about thinking beyond resonators, because resonators take up a lot of space on a chip, and maybe taking ideas from capacitance readout in classical electronics. I was wondering if you could maybe say a little bit about that as well.
Yeah, sure, Jonathan. Thanks for the question. And I think it goes a little bit along the lines of what Joe's presented today, particularly when he saw the demonstration of readout of individual electron spins associated to donors in silicon. So in that slide, you could see that the technique used for readout was an ultra-sensitive charge sensor. That's a method that's taken us very far. But the method that I focus a big part of my research on is an alternative method that is known as dispersive readout. Basically, you forget about your charge detector, and then you embed your quantum system of interest into a resonant cavity, and you probe the resonant cavity rather than a separate sensor to detect the state of your quantum system. In both cases, you need to transfer the spin information into a charge degree of freedom, because we are not very good at reading the spin, but certainly very good at reading charge moving. So just to put this, trying to put this a bit in perspective, no? But certainly dispersive readout brings the advantage that you don't need those extra charge sensors in your architecture, in your device layout, that, for example, in quantum computing may break some of the connectivity that you may want to have in a large-scale quantum computer. No? So, for example, if you are thinking of two-dimensional arrays of qubits, bringing in charge sensors, at least in the plane, will certainly break that symmetry. Whereas with dispersive readout, you can use the gates that define already your quantum systems and connect them to those cavities to perform the readout. So certainly we like this feature of the technique, because we believe that it's going to be the technique that is going to allow us to have higher connectivity in quantum computing architecture. So we are really trying to push this. I believe at the time of reading or writing the roadmap, there was already a very exciting work that came out from the Van der Sijpens group at the University of Delft that showed that with this technique, you could get certainly high readout fidelities of 97% in just a few microseconds. But following some of the guidelines that we put forward in the roadmap, my colleague David Iverson and I, we've been able to push down this figure and achieve an electrical fidelity down to up to 99.7%. Most importantly, in just 300 nanoseconds. No? So things are getting quite fast. And we are doing now some experiments that tell us that certainly this figure can be dropped by another factor of 10. No? So I think tens of nanoseconds for a high fidelity readout beyond the fault tolerant thresholds is certainly within reach. Beyond that, things may start to become a bit complex, no? So we will need to think whether we want to push it further. But one of the things that we need to take into account is maybe how fast you would like to go, no? How fast you need to go, no? In your quantum processor. And I think here the answer is, well, what is the slowest step, no, in your computation? Is it your 2-qubit gate? Is it your 1-qubit gate? And just to put as a reference, in electron spins in quantum dots in silicon, for example, 1-qubit gates are of the order of, or it will take you of the order of a microsecond or so to perform. No? So I think with dispersive readout, we are doing quite well. Certainly it's not going to become the bottleneck, which I think is something that we want to try to avoid. And yeah, I think one of the benefits of this is that will certainly it allow us to perform readout while computing, no? Whereas other quantum computing architectures may postpone readout towards the very end because of the slowness of the readout. I foresee that dispersive readout will enable us to read while computation is happening. So things are looking quite good. What else? So you also ask about one of the aspects of dispersive readout, no? That is that they rely on resonant cavities, no?
Right.
And that these resonant cavities occupy substantial space. No? And one point that we touched upon on the roadmap was to see, or was to think, no? Whether there is something that we can do about the footprint. Maybe for the audience as well, to put this in perspective, the current cavities that are used for readout of spin qubits are of the order of 1,000 times or even 10,000 times larger than the qubits themselves. No? So that poses a major footprint bottleneck. But I think we already in the roadmap touch upon some routes that may allow us to reduce the size of these resonators, such as the use of high kinetic inductance materials, or maybe something that we will touch upon later, rather than parallel readout or frequency multiplexing, the use of time division multiplexing, no? Using the same resonator to read many, if you can read fast. And you also talk about inspiring ourselves on what is done in the silicon industry for reading out a small amount of charge. No? We see every day that in our laptops, dynamic random access memories are read with high reliability, and the capacitors that form those memories are quite small. No? So I think techniques that are based on pure electrical circuits, pure amplification at the chip, may also help us in reducing the footprint. No, this is, I think, still very, very early days. Certainly, dispersive readout works very well, no? So that's why we're sticking to it. But I think there are opportunities, no, to inspire ourselves on what is done in the semiconductor industry.
Yeah, good, great. Yeah, it's really exciting to think that, tens of nanoseconds, high fidelity readout of spins. I mean, that's quite impressive. And yeah, thinking, based on what's going, already being used in the CMOS industry, that just seems like a further path for sort of integrating quantum and classical technologies more, which is, I think, a good direction to go in. So, okay, thanks. Then I'll ask a question to Jan, who wrote about single molecule devices in his roadmap article. So device variation and reproducibility is, of course, a challenge for all quantum nanotechnologies, and maybe particularly so for single molecule devices, despite the fact that they hold a lot of promise in principle. So you wrote about how molecular networks might mitigate this problem to a certain extent by having transport through many molecules in parallel, kind of averaging out the variations. So what are some of the practical applications people have in mind for these kind of devices based on molecular networks? And what benefits of the single molecule transport do they retain?
Right, yeah, that's a very good question, Jonathan, thanks. So molecules are an interesting challenge that on the one hand, they give you the sort of atomically precise engineering that you want. So as Joe was showing in his presentation, some of the work from Sydney where they're able to place a single phosphorus atom in a silicon lattice with atomic precision. Chemists can do that as well. Synthetic chemists can make atomic structures with atomic precision. They can put the atoms exactly where they want. They can build a structure around it. And they can do this at scale. They can make Avogadro numbers of these structures. The problem is that all these structures are exactly the same up till the point where you try to make a device out of it. Because as soon as you try to make a contact to it, depending on how the molecule sort of binds to the rest of the device architecture, it will behave very differently. So one sort of way to circumvent this, I guess, is to to acknowledge the fact that there will be variability from one junction to the other, and try to make use of sort of ensemble properties of these molecular junctions. And one way to do that would be to, well, there's different kinds of sort of self-assembly techniques that you can make use of. One of them would be, for instance, to couple your molecules to nanoparticles, where you make ordered networks of nanoparticles linked via molecules, and then you can make use of the optical or the plasmonic properties of these networks. Of course, then you're limited to kind of ensemble type experiments. Similarly, if you use metallic organic frameworks, which are sort of crystal structures made up of interlinked molecules. So any sort of technology that relies on ensemble averaging, I think you could get away with these kind of ordered networks. Of course, if you want to do the kind of things that Joe was showing earlier, where you use the spin of a single ion or a single atom, then you can't do those kind of experiments, and then you have to come up with ways to actually make see if there's ways in which you can make these molecular junctions in a reproducible way, and there I guess the key would be to so at the moment the problem is that, as I said, the molecules themselves, they're all exactly the same, and they're made with sort of atomic precision. The problem is when you couple it to the electrodes and when you couple it to the other structures. And one way around this, and you see this sort of move towards that in synthetic chemistry now, is to make larger molecules. So, for instance, there's been a lot of work recently on graphene nanoribbons, which are essentially sort of large conjugated pi systems. So depending whether you're a physicist or a chemist, I guess. If you're a physicist, you'd say they're small bits of graphene. If you're a chemist, you say they're sort of macromolecules. But what they essentially are is a strip of graphene with functional groups at the edges of the graphene, and they are large enough, so they are on the order of sort of tens or 100 nanometers even, that you can interface them with nanoelectronics that you can fabricate using conventional lithography methods. So I think if you want to go towards sort of single molecule devices where you really take advantage of the properties of single molecule and the fact that they are synthesized with atomic precision, then I think you have to go to these larger molecules and try to interface them with conventional lithography techniques.
Yeah, great, thanks. And I know that you work a little bit on, you like the idea of building thermoelectric devices with these molecules. So would the ultimate goal of that be sort of power generation, that kind of idea?
Yeah, so with thermoelectric devices, there's an interesting sort of convergence of two different fields, I think. So on the one hand, people have been looking at making thermoelectric materials, and one of the key challenges in making thermoelectric materials is that some of the parameters that determine the efficiency of a heat engine or a thermoelectric generator, some of those parameters are contraindicated, meaning that if you optimize one, you decrease the other one. So for instance, you want to have high electrical conductance, but if you have high electrical conductance, you have also high thermal conductance, which makes your generator less efficient. And the way around this is by nanostructuring it. So people found that if you make these thermoelectric generators out of nanoscale junctions, then you break the link between those contraindicated parameters. So that, from the one hand, people have been sort of working towards scaling down these devices for thermoelectric generation. On the other hand, there's the field of quantum thermodynamics, which is looking at sort of thermodynamics of quantum systems. And as it turns out, the kind of devices that you need for that are very similar to the sort of thermoelectric generator devices. So there's a very interesting sort of convergence of these two fields. And recently we published a paper, for instance, where we use a thermoelectric device, a single molecule thermoelectric device, where we're actually able to measure the entropy of a single molecule. And the entropy, of course, is sort of one of those classical quantum or classical thermodynamic properties. You know, it's the heat divided by the temperature. But in fact, we can measure this for a quantum system, which is the spin of a single molecule. So it's a very interesting research direction.
Yeah, no, that's very exciting. Thanks. So now let me ask a question for Wei. In the roadmap, you wrote about 2D magnetic materials, but I know that your work is more general than that. Similar to Adina, you work on lots of these van der Waals heterostructures. So having this ability to create van der Waals heterostructures by deterministically placing 2D layers on each other, you really have an unprecedented toolbox for rationally designing these nanoscale materials. What are some of the frontier ideas on engineering quantum materials with desired electrical, magnetic, and optical properties? What are the long-term applications that you're most excited about?
Thank you, Jonathan. Can you hear me?
Yep.
Okay, thanks for that question. So yeah, let me just quickly say that our section that we wrote about fell under low dimensional materials, but we specifically talked about 2D magnets, and this is perhaps a rather small subfield, but given the space constraints, right, that's what we decided to do. But it indeed falls under this larger category of 2D systems. So I can give you a brief history, right? I think most of us know about graphene and these 2D semiconductors. But even from the very beginning, I would say people wanted to use those same exfoliation methods to look at 2D systems from other layered compounds, right? So having a van der Waals material as the bulk, that's a very common structure for many things, right? But however, there were some technical challenges of why things like 2D superconductors and 2D magnets came later on. And probably the biggest one is that unlike things like graphene, boron nitride, transition metal, dichalcogenide semiconductors, these materials are rather unstable. They can degrade in the air, or they can even react violently with the air. So it wasn't until people realized that you need to prepare these materials, stabilize them within an inert environment of a glove box before these things became possible. Okay, but the idea itself is not new. As far as your question goes, right? So indeed, if you can stack different 2D materials on top of each other, like Legos, that gives you an unprecedented degree of control over traditional thin film systems, right? If you think about growing heterostructure with MBE, then you're faced with constraints like surface cleanliness, lattice matching, and you cannot just put A on top of B randomly, right? Here, right, even though we're dealing with layered 2D materials, right, essentially that there's a lot of them in existence, and we can combine them together, without these constraints. So it gives us a lot of flexibility. And of course, if you put A on top of B, you can imagine that your heterostructure would have the properties of A and also have the properties of B, right? So I guess that alone is useful depending on your application. But I think what is perhaps more exciting is if you can have something, put two things together and get some property that's beyond the sum of their parts, right? So if there's something interesting happening at that interface, that gives you some emergent property, right, that you can take advantage of, right? That's something that's really novel. So that's one thing. And then the other thing I think is very exciting is something that Adina already touched upon, right? And that is unlike NBE film growth or even these other traditional film growth methods, we have control over the twist angle, the relative twist angle between 2D systems. And as Adina just described, that is actually a very non-trivial knob, right? So she gave you the example of twisted graphene, and you can have these flat bands giving you superconductivity, magnetism, etc., right? But there are other ways that twist angle can affect things as well. So for example, in 2D magnets, one thing that we know is that the interlayer magnetic coupling, right, can be, depending on the system, but let's say for simplicity, it can be antiferromagnetic or ferromagnetic, depending on that stacking, right? And by essentially twisting it, you're changing the stacking on this moire length scale, right? So you can have a system where you've sort of designed your a domain structure with different types of magnetic textures, and that's something that also can be useful. Sorry, I might have forgot. You asked a lot of things there, so I might have not touched upon all of them. But if you like me to answer,
no, that was great. Any long-term applications that you can mention?
Yeah, so applications is a tricky one, right? So the quality of these 2D crystals, I would say, are excellent, right? And compared with more traditional films, they're a lot more intrinsic. So you don't have to, you might still have to deal with these issues, but not nearly to the same extent. For example, you don't have to deal with grain boundaries. You don't have to deal with defects as much. Right, and so just by exfoliating them and putting them on some substrate, you have an ultra clean 2D system that you can study, right? So there are a lot less materials issues that you have to worry about, right? So you grow a film, right? Oh, it doesn't behave the way that you want it to. What's the cause of that, right? Is it because it's too defective and so on? So you have to characterize that. So that's the advantage. The disadvantage is that exfoliating these single layer crystals is not scalable, right? You can have, it's a great way to do device prototyping, right? So we can do it at speeds that someone who's growing large scale films can't. So we might be able to determine what is a device prototype that has a high potential, right? But then, you know, if someone wants to make a large-scale device, or even maybe down the line commercialize it, they need to figure out how to grow a very high-quality film of that material on ideally the wafer scale, right? And there are indeed people that are tackling these problems, but that comes with time, right? So I think right now people have figured out how to grow these semiconductors on the wafer scale with pretty high quality, and hopefully, you know, eventually down the line, these technologies, techniques, I should say, would come to things like 2D magnets as well. And then that's something I'm hoping for.
Okay, great, thanks. And maybe there are some applications where you don't need scalability, right?
That would be true if you have a magnetic field sensor with excellent high quality, and then if you can put that on a scanning probe or something, then one is enough, right? Yeah. But I don't have all the answers there either, so there are challenges there as well.
Okay, great, thanks. So there's one question from the audience, which is probably directed more to Joe or Fernando, somebody thinking about sort of scalable quantum computing architectures. What are the challenges you'd expect to face with this technology if using lots of these physical qubits to build a topological code? So that's a pretty general question. Anybody can jump in on that.
Fernando, you want to take that?
Yeah, I mean, I think it's a general challenge not to perform error correction on with a combination of physical qubits. I mean, we've seen very recently a couple of very promising demonstrations from ion traps and from superconducting qubits. Maybe what I can comment a little bit more in is silicon spin qubits. No? What are the prospects of this? I mean, maybe to say silicon spin qubits are a relatively recent field, and it is only until this year, that 2-qubit gates have been demonstrated to the levels of fidelity that are necessary for error correction thresholds. This is 99% fidelity or more. No? And we are still waiting for a demonstration of that in a single chip, in a single piece of technology, we can reach 99% in all the different steps of a quantum processor. No? Initialization, 1-qubit gates, 2-qubit gates, and readout. So these have been demonstrated independently, that this is possible with pushing the best approaches for obtaining high fidelities on every single one of those steps. But it becomes challenging to do all of those well in a single structure, and also to scale those up, such as you will not only need to do this in 2 qubits, but in a good number of those. So what have we learned? That we can do all those steps independently, we can do them well, but it's about putting things together and scaling up. So there is and I think this is a general challenge. It's a challenge for me. I presume that also for you, Joel, will be a challenge, but for any technology, scaling up while maintaining high levels of precision in all the operations.
Yeah, great.
Yeah,
something like this. Oh, sorry, go ahead, Joe.
I would pretty much agree with that. I would say, like, physicists are really great at optimizing one thing in one experiment and writing a paper about it, but they're not very good at engineering a system. You need engineers to do that. So I think it's a real opportunity for people who are interested in, driving the engineering of the architecture. I want to add to what Fernando said by saying that I think there's a massive challenge with materials that needs to be overcome in the spin. I mean, despite the fact that you see all these Nature papers, even if you look at Intel's spin qubit devices produced in a foundry, they're going to have the same problems as the ones in universities, which are related to valley splitting and size of quantum dots and this MOS approach. That's why I think the MOS approach is really going to have to rely on material development. So yeah, there's the architecture and materials and instrumentation. All these things need to be pushed and need to keep being pushed. But it, you know, I want to add that it does. There's one interesting thing I think about spin qubits, which makes them maybe not, the fact that they're not so different from superconducting qubits from an instrumentation point of view. I think that's a nice thing about spin qubits. You know, that you know, if you had to kind of develop a whole new kind of infrastructure around it, there would be probably a lot more resistance to developing that. You know, the more you can leverage someone else's hard work, the better. So I think the future looks promising for them. They're small and coherent, but yeah, there's a lot of challenges ahead, and they're not necessarily the kind of challenges that physicists are very good at. So we need a lot more people in this field with different perspective.
Yeah, I agree. Any other comments? I would just say, since the question mentioned topological codes specifically, you know, another challenge, if you think of a large scale surface code, is just extracting all the information that you need, you know, per second from these ancillary qubit measurements. Even if you can measure them out, you know, on a time scale of 100 nanoseconds or something, you still have to get like terabytes of data, and it's really hard to know how that's going to happen. If you had millions.
Yeah, that's why going slower might be better.
Right. So that's where you need the long coherence times that Joe was talking about.
And let me add to that, Jonathan. And not only just getting the data out, you don't know what error happened once you got the data out. You have to process the data using rather sophisticated algorithms. So yeah, implementing a topological code is a fearsome challenge, but you know, it's extremely exciting because of the properties of topological codes. So it'll be worth the effort.
Yep, great. Pierre, do we have time for maybe just one more general question for the panel? We're a little over. Sorry?
Go on, yes. Just
okay.
burning question.
So I think since we're kind of running out of time, I'll just ask a simple question and maybe everybody can chime in. What are the applications for which quantum nanotechnologies will most impact society in the next, say, 10 or 20 years, just to pick some number randomly? Maybe we can just go kind of one by one. So Adina, what do you think?
I will take my physicist place in this panel, and I will say that at least for the systems that we spoke about, you see, as condensed matter physicists, our job is to understand any material that we have. And I think a lot of these platforms are really pushing the boundaries of what we understand about quantum matter and all the phenomena that happens at these time scales and length scales and energy scales and so on. And so I think it's quite at least in our field of 2D materials, quite exciting to be able to have so many control knobs and create these condensed matter systems that previously you cannot encounter in nature or create them. So I'd say we're excited about that for now.
Okay, so sort of like simulating physics, new physics. Okay, great. Jan?
Yeah, I would agree with Adina that you know, understanding nature is one of the key drivers for physicists. Obviously, I think one application that I think is sort of in the nearer term is probably sensing. So there are a lot of things that these systems are sensitive to. So again, a lot of the stuff that you don't want for a quantum computer because it introduces noise. It's actually, if you want to detect that kind of stuff, that's useful. So I think in a sort of shorter term, using it as a sensor could be quite useful.
Great, yeah, I agree. Fernando?
Yeah, I mean, certainly with that time scale in mind, I will say that it'll be great to see quantum computers making an impact in society. They are evolving at a very good pace, no? And they are already solving problems that the most powerful supercomputers on Earth cannot. No, these are made-up problems, no, for quantum computers that to make them excel. But things are not looking very bad in medium to long term to see a quantum computer solving a useful problem. No, so I think that's going to happen sooner or later, and I think it's going to change our life. And the other point is maybe on quantum sensing. No, as Jan was saying, I mean, something that I find fascinating that it's been a bit of a side product of quantum computing research is quantum limited amplification, parametric amplifiers that, I mean, if you talk to an electrical engineer and you say that you have an amplifier with an equivalent noise temperature of a few hundreds of millikelvin, they'll think you're joking. No? So certainly these instruments are not only useful for quantum computing, but are going to be useful for other applications. You know, some colleagues are even using this for dark matter research. No? So the applications, I think, are going to be unimaginable now, and we will see certainly.
Yeah. Okay. Great. Thanks. Wei?
Yeah. So as far as 2D materials are concerned, I echo what Adina said, but at the same time, I want to say that if we sort of broaden our definition of quantum a little bit, right? I mean, I think 2D materials are already being used in technologies, right? Like displays and so on, and actually quantum dots as well, right? So in a way, it's already here, right? It's just, you know, you're really looking towards the frontier when you say quantum and nanotechnology, right? So there I'm also a bit unclear. But I should say if we want to talk about other nanostructures, right? I think, Jonathan, we have a mutual colleague who's using nanowires to do single photon detection, right? And I think quantum communication, that's perhaps one of the nearer term applications of quantum technology. And there, I think, you know, people have already shown that these are, you know, these devices in a way are outperforming other devices, and they are scalable, right? So.
Yeah. I mean, also as sources, photonic sources.
That's well. Right. Sources as well. Yeah.
Okay. Thanks. And Joe?
Thanks, Jonathan, and thanks everyone. Yeah. So. I think one of the things that most excites me about quantum nanotechnology, let's say in the domain we're discussing with solids, is that, you know, you have regular classical technologies that can co-evolve with quantum technologies, from computing photonics, say classical, to quantum computers and quantum networks, you know, and the like deeply on the quantum mechanical side, and that together. So what impact this can have, I would agree with the panel that these two technologies co-evolving together, it can push applications and just in regular computing, sensing, photonics, and we can get a whole new class of computers out of this. 10 to 20 year timescale, I think it's doable to have useful quantum computers. And, you know, the offshoot of that, which I'm very interested in, is, you know, as quantum information evolves, these tools that we learn from this will feed back into fundamental physics as well. Not just using quantum computing or quantum materials to learn more about nature, but also developing tools to that we didn't have before that help us to attack problems in a new way. So that's, I think it's something, just the ability to harness quantum mechanics like this. You have so much that you can do both on the applications and fundamental side. It's a very exciting field to be in right now.
Great. Well, I think that was a great way to finish off the discussion too. So I think we're kind of out of time. Kara, did you want to say some closing remarks? And thank you, everybody. That was a really fun discussion.
Yes, thank you. Yes, absolutely. Thank you very much for the excellent talks and the insightful discussion today. It's been really fantastic hearing all of that. As a reminder, the roadmap can be found on our journal homepage. It's open access, so freely accessible by everyone, so check it out. I would like to obviously thank Jonathan for facilitating today's session and for helping us organizing the webinar. Thank you, Joe Salfi, for your excellent talk, and also obviously all the panelists for the participation and the interesting discussion. I would like to thank again all the authors of the roadmap, and a special thanks to the other lead author, Dr. Arne Locht, whose contribution has been instrumental for the setup of this webinar. Finally, I would like to thank all the attendees today who came along, and obviously those who asked questions. So I think this is the end of our webinar. Thank you very much. Goodbye, and see you the next time.
Bye, everyone.
Bye, everyone.